When dealing with volumetric glassware, there's two different designs you should know about. There are glassware that is calibrated to contain a particular volume, and there's other glassware that is calibrated to deliver a particular volume. And the idea being that when you pour out liquid from the to deliver glassware, some of the liquid adheres to the inside glass surfaces, and so it doesn't actually come out. And the calibration to deliver accounts for the fact that some of it gets left behind. If you're making a solution, then it turns out that you need to know the total volume inside the glassware. Whether you can pour it all out or not is irrelevant here. And so TC is typically what you look for. If you look at this volumetric flask here, you'll see a couple of things. You'll see the mark here, which represents the 500 ml line. The meniscus of the liquid has to be carefully lined up, so the bottom of the meniscus is level with the mark. So if you're looking at it side on, you should just see a single line here, but if you're looking at it above or below, you will see two lines, so that's one way you can tell. If you look down here, you can see it says TC 20 degrees C, so this is actually calibrated to contain 500 milliliters at 20 degrees C. So the other thing, the 20 is important because it tells us the temperature at which the calibration is carried out at. And the importance of the temperature is that if you heat up the glassware will expand, and so the volume is no longer exactly the same as it was before. So you really need to either do everything at 20 degrees C, or as we'll see in one of our first labs actually, we need to know how to correct for the actual temperature of the lab and the calibrated temperature. So the TD is typically used for things like pipettes. It's also used for things like cylinders because you are pouring out the liquid in there, and burettes as well. So TC is typically used for volumetric flasks. One of the problems with glassware is that the surface of the glass is essentially something that looks like this. So we've got these OH groups on silica, and you can find particularly cations, so X positive, can bind to these hydroxyl groups on here and can stick and can contaminate your sample. So one way we can remove this is we can actually do an acid wash. We can wash with something like 3 molar hydrochloric acid followed by a rinse with water, and this will actually exchange the cations for hydrogen ions. So if you're okay with having hydrogen ions but not sodium ions or potassium ions and whatnot, this is one possible way you can remove surface contamination. If you have brand new glassware, one of the things you might get used to in the lab is actually soaking it in acid for about an hour, followed by a soak with deionized water. You can use polypropylene glassware as well, so you can get polypropylene volumetric flasks. And the nice thing about polypropylene is it doesn't have these OH groups on the surface that can bind very small amounts of metal ions to, and so you don't have to worry about trace analysis issues here. The problem is that if it scratches or if you heat it up, the volumes can warp slightly, and so glassware is just a little bit more robust to work with. When working with pipettes, it's nice to know that there's actually two different varieties that you'll find. There are transfer pipettes, which are probably the most common pipette in a chemistry lab. And this top pipette here, pipette A, is an example of a transfer pipette. They are calibrated to deliver, so this one here is a 10 milliliter to deliver pipette. Underneath you've got a measuring pipette, which is very similar to a graduated cylinder in that you can transfer variable amounts of volume, and it is calibrated in such a way that the volume delivered you can figure out by taking the final volume measurement minus the initial volume measurement. Now, the Class A version of these pipettes has a pretty decent tolerance, so the volume in milliliters, okay, for a 1 ml pipette has a tolerance that is an allowable calibration error of plus or minus 0.006. If you had, say, a 5 ml pipette, plus or minus 0.01, a 10 ml pipette, plus or minus 0.02. So you're looking at 0.2% error for a pipette like. Now, one of the things to remember with a to-deliver pipette is that you should never blow out the last drop of the solution because it's calibrated to leave it behind. We'll use a special pipette bulb in our class in order to suction up liquid into and out of these pipettes. And when we empty the liquid from the pipette, we will essentially push this button right here. And essentially it allows air to flow in this valve and down the pipette and allow the liquid to drain out. But notice we will never squeeze the bulb and push every last drop of liquid out, otherwise that will deliver a little bit more than the pipette is calibrated.